Example D, log of 1 over x to the 6th times y minus 3 to the 7th. So this is equal to, I am expanding over addition and subtraction, pulling down my exponents. This is log of, the guy upstairs is 1, which is why log of 1 is a positive, minus log of x to the 6th minus log of y minus 3 to the 7th. And I guess this could be in more parentheses if you wanted, or technically they should probably be brackets, but I don't like brackets because it's hard to know when you need them ahead of time. Anyways, okay, so again, anything that comes from upstairs is positive. Anything that comes from downstairs is negative. Downstairs being multiplied together, both become minus, and I am just going to cut to the chase from here on out. Next, log of 1. What I am supposed to be asking myself here is log, I should know, is base 10, and 10 to what power equals 1? Or is it even possible for 10 to some power to equal 1? My vote is yes, because 10 to the 0 is 1, which makes our exponent here 0 minus 6 log of x minus 7 log of y minus 3. And my final answer here would be negative 6 log x minus 7 log of y minus 3. Now, last thing that I want to point out here. Why doesn't log of y minus 3 turn into anything? Because addition or subtraction inside of a log is nothing outside of a log. Multiplication and division inside is addition and subtraction outside. Addition and subtraction inside is nothing outside. And especially in this class, they want to make sure that you know that, so they will put guys with addition or subtraction inside of there on purpose. Okay. Example number 2, now we're going to go the other way. We want to rewrite as a single logarithm. So we're going to go in the exact opposite direction. So before we addition and subtraction first, pull down exponents second, I'm going to go exactly opposite, pull up exponents first, condense down the addition and subtractions to multiplication and divisions inside. So example A, 3 log base 7 of x plus 4 log base 7 of y minus 8 log base 7 of z. Step 1 is to pull up my exponents. So this is log base 7 of x cubed plus log base 7 of y to the 4th minus log base 7 of z to the 8th. We are going to leave positives, well, positives stay positive, but we're going to leave the minus down below because that minus just means that the z to the 8th goes downstairs. What if instead of a minus this was a plus? Well, then I would just condense it down to all multiplication inside, and there would be no fraction bar. But because we do have a minus here, if there is a negative, then you have a fraction bar when you condense them down into one logarithm. Okay, so this is going to equal, I'm going to condense over my addition and subtractions all at once. This is log base 7 of one big logarithm. Again, how do I know I need a division bar versus how do I know if I don't? If they're all positive, no division bar. If you have positives and negatives, it means you have guys upstairs and downstairs and you need a division bar. So who's positive and going upstairs? That's x cubed y to the 4th. Negative, so going downstairs is our z to the 8th. And Oh, I was going to say one other thing. Oh, everything that gets condensed inside is connected by multiplication, either on top and or bottom. And log base 7 of x cubed y to the 4th all over z to the 8th. I feel like all over what x cubed y to the 4th over z to the 8th is our answer. Okay, example B. Log of 7 minus 2 log of y plus 1/3 log of x minus 10 log z. Again, first step is to pull up any exponents. There's no exponent on log of 7 minus log of y squared plus log of x to the 1/3 minus log of z to the 10th. Once I have pulled up my exponents, then I'm ready to condense down into one logarithm. Again, do I have a division bar or not this time? The answer here is yes, because I have at least one negative. In fact, I have two of them, so that means that two guys are going downstairs. So who is upstairs? The positive guys go upstairs. That is 7 and x to the 1/3, or the cube root of x, you will need to change it to for your final answer, divided by, who is downstairs, y squared, z to the 10th. And this is our answer. Okay, example C is 2 ln 5 plus 3 ln x minus 1/2 ln of 2x plus 3. And first up here, I need to distribute this 2 for a 2 ln 5 plus 6 ln x minus 1/2 ln of 2x plus 3. Okay, now I'm ready to pull up my exponents for an ln of 5 squared plus ln of x to the 6th minus ln of 2x plus 3 to the 1/2 power, even though my 1/2 came out weird. Let me try again. That's better. Okay, once I've pulled up my exponents, then I'm ready to condense down into one logarithm. Oh, I do need a division bar here. All right, so let's just change this one to plus. So that way we don't need a division bar this time, because they don't all need a division bar. So no division bar this time because I just changed it. But we're going to have 5 squared times x to the 6th times 2x plus 3 to the 1/2. Or we're going to make our 5 squared into a 25. Then we have our x 6th. And then we have our square root of 2x plus 3. And this is our final answer this time. Again, there will not always be a denominator. If they are all positive, like I changed this guy to be, then no division bar needed. Okay, example number 3. Our directions are simplify. Now, couple different things. Log base 2 of 2 to the 21. Could you pull down the exponent and simplify it that way? Sure. We actually did a problem similar to this previously. We said, okay, 2 to what power should give me 2 to the 21? Oh, well, question mark needs to be 21. But even easier than that is log base 2 of 2 to an exponent, and log base 2, those 2's cancel, or log base 2 of 2 cancels, and 21 falls out. All done. That's what this property here says. Log base b of b to the n, log base b of b cancels, and n falls out. And we are going to use this property a whole bunch in the next section. Same thing with b raised to the log base b. So you just have to keep in mind that exponential functions and logarithmic functions are inverses when they have the same base. They're both base b here. And this is an exponential being raised to a log base b. So log base b of b to the n cancels and falls out. B raised to the log base b of x. B raised to the log base b cancels and x falls out. Okay, so equals 21, and then we don't even need any of this side work stuff when our base matches up. Okay, so what about 3 raised to the log base 3 of 15? 3 raised to the log base 3 of 15. Well, according to that property up there, 3 raised to the log base 3 is supposed to cancel, and 15 falls out. All done. Now, I do usually in class give students this problem to try before I give them those last two properties. And how are you supposed to figure out 3 to the log base 3 of 15 is equal to 15 without knowing that property? And it is a little tricky, but I am going to explain it to you real quick before we move on to the last little bit of this section. If you were just to look at log base 3 of 15 on its own, 3 to some power that we know of doesn't equal 15, or 3 to a power that we know of will not give us 15. 3 to some power does equal 15. It's just not a nice number, or it equals approximately 15 because we would have to approximate it. Anyways, but this equals the number you raise 3 to in order to equal 15. And when I do 3 raised to the log base 3 of 15, or I'm saying that this is 3 raised to the number you raise 3 to in order to equal 15, well, I'm taking 3 and raising it to that number. So what is it supposed to equal? 15. And I'm just going to let that marinate for you. And I'm not going to try to explain it any more than that. I am going to pause my video. We're going to get another helpful tool into our tool belt of things that we can use to evaluate our logarithms. And then that's the end of the section. So let me pause my video.